following examples. So when we last left off, we were looking at resonance effects on a molecule's stability. And generally, the greater the amount of conjugation and the greater the amount of delocalization of a molecule's electron density via resonance across multiple atoms, the more stable that molecule would be. So just to get us back in the rhythm of things, which of the following molecules would you expect to experience the greatest amount of resonance stabilization? The structure on the left or the structure on the right? Which of the following molecules experiences the greatest amount of resonance stabilization? The structure on the right is quite a clear winner. So first, it's aromatic. And it has the greatest number of conjugated atoms, and so our electron density is distributed over a greater number of atoms, which is more readily able to stabilize that electron density. So looking at the following example, so we have a pair of two cations. And which of the following cations would we expect to be more stable? Which of the following cations would we expect to be more stabilized via delocalization? The structure on the left, as we have a greater number of atoms to distribute our electron density over. The major contributing structure for this cation that partially results in its pretty large stability has to do with the following resonance structure, where despite the fact that this structure does not fully obey the octet rule, this structure is a major contributor, oddly enough, because our ring has 6 electrons in our conjugated cyclic system, and so we have an aromatic cyclic system. Comparatively, this ketone on the right, one of its contributing structures has 4 electrons and it's anti-aromatic. You don't have to worry about this aromatic and anti-aromatic discussion quite yet, but it does have a pretty marked effect on stability. In this case, as we can see, this positive charge is stabilized because it can be delocalized across all the atoms in our cyclic system. So everyone was correct in selecting the cation on the left to be more stable than the cation on the right. And now to tie things back to acid-base chemistry, let's look at the following example and let's ask which of the anions would you expect to be more stable? The anion on the left or the anion on the right? Which anion is more readily, is easier to form and is more stable? The anion on the left, exactly right. The reason for that is we can delocalize our electron density across both of our ketone functionalities in conjugation, and in turn stabilize this negative charge. In the structure on the right, we're stuck. We can only really delocalize our electron density across one of our ketone functionalities. And this difference in anion stability has a direct impact on the observed pKa, or the acidity of the protons attached to that carbon. So resonance effects do play a pretty big role in anion stability, and it's closely tied to the idea of acidity and basicity. Do these examples make sense to everyone so far? Do these examples make sense to everyone so far? Any questions on these examples? If not, let's look at some examples that are a little bit trickier. So let's look at the following molecule, and just to make sure that we're comfortable with the concepts that we covered in the resonance section of this chapter, let's look at the following molecule, indicate the hybridization of each atom. Let's draw one major resonance structure and indicate the delocalized and localized lone pairs, and finally indicate the geometry of each atom. So let's work on this example, which is just a capstone review of our section on resonance, and then we'll discuss this example in about 4 to 5 minutes. And don't be shy to use the annotate tool to share your proposed responses for the major resonance structure for the following molecule. Additionally, if you could focus on identifying the hybridization and geometry for each of these 4 indicated atoms, and you're welcome to communicate the hybridization and geometry for each of these atoms in the chat. And we'll discuss this example in about another 3 to 4 minutes. Just as a reminder, the annotate tool is accessible from the meeting options tab, which is a little black tab under the Zoom viewing features. At the bare minimum, we should be able to communicate and talk in the chat about the proposed hybridization and geometry for each of these 4 atoms. And if you have any questions, don't be shy to ask them in the chat or verbally. And let's try to get a few more responses in the chat before we discuss. And does anyone have a proposed response for the hybridization of any of these 4 atoms?
Oxygen is sp2.
Which oxygen are you referring to? 3 or
the very top one.
okay. 4. We have a proposed assignment of that this oxygen is sp2. Does anyone else have an assignment for any of the hybridizations for any of these 4 atoms? Nitrogen number 2, we have a proposed assignment that it's sp3. Okay. Do we have any other assignments for these other atoms in this molecule? Don't be shy to share it in the chat or verbally. So 1, we have a tentative assignment that is sp3. Does anyone have any other assignments for the hybridization for any of these molecules or any of these atoms in this molecule? Okay, so we've seen a range of responses in the chat. So let's discuss now. And the first thing we need to do is we need to draw some of the resonance contributors, because depending on how our lone pairs are delocalized, these resonance contributions can affect the observed actual hybridization of atoms in our molecule. So we can draw a major resonance contributor where we've delocalized our nitrogen lone pair into our adjacent pi bond. So we form a carbon-nitrogen double bond, and our carbon-oxygen double bond is broken to generate a lone pair. This is a classic resonance structure for amide motifs. Okay, perfect. Now, what is this resonance structure telling us? Is this nitrogen entirely sp3, or does this nitrogen have some sp2 character? So we see in one of our resonance structures, our nitrogen is planar, has an sp2 hybridization. So in order for this lone pair to participate in resonance, what must the hybridization of nitrogen number 1 be? It must be sp2, because otherwise the nitrogen lone pair would not be placed in a p orbital, and it won't be able to engage in resonance delocalization. So remember, resonance effects directly impact the hybridization of atoms adjacent to those pi systems. The nitrogen lone pair is delocalized via resonance, and the only way the nitrogen lone pair can interact with our adjacent pi system is if it's in a p orbital. Does that make sense to everyone? The other assignments look fine. This nitrogen is isolated. It's a localized lone pair on nitrogen. That's why we have an sp3 hybridization. This nitrogen lone pair is delocalized, and that's why we have an sp2 hybridization. 3 is still stuck with an sp3 hybridization because it's not directly adjacent to a pi system. And so it cannot experience a significant amount of resonance delocalization. So these oxygen lone pairs are relatively localized. Now, in terms of geometry, one consequence of this resonance contribution is that this sp2 nitrogen is trigonal planar rather than trigonal pyramidal. Amides are flat for the most part. Comparatively, for this nitrogen, which does not experience resonance delocalization, our lone pair is relatively localized, our hybridization is sp3-like, and we have a geometry of trigonal pyramidal. Finally, what would the geometry of this oxygen be? What would the geometry of the oxygen down here? It would be bent, exactly right. Does this example make sense to everyone? So you always need to start, when you're analyzing a structure, you need to start by drawing out the resonance contributors and identifying major and minor resonance contributors. Does that make sense to everyone?
On the test, would you also want us to indicate the hybridization of the carbons on the structure too?
Yes. But for that, it's pretty mundane in that one of the carbons is sp2.
And the rest of them are sp3.
Yeah,
Okay.
Mhm.
What about the oxygen on the top? Would that be like a linear structure or?
So it's sort of odd to talk about geometry if there's only one attached atom. I guess you can say that it's trigonal planar like, but unless there are multiple attached atoms, it's sort of a shorthand to discuss hybridization and geometry.
Okay.
So this oxygen, you can view it as sp2 like, or you can think of this oxygen as unhybridized. Both interpretations would lead to the same conclusion and um, a very similar bonding arrangement. I'd say this oxygen, in terms of geometry and bond length, behaves very similarly to an sp2 hybridized atom. But in terms of geometry, as there's only one attached atom, we can't really talk about like bond angles, for example.
Right. Okay.
But you can say it's like trigonal planar like, and that would be perfectly fine.
Makes sense.
Perfect, perfect. So let's now talk about acid-base chemistry. And you're really going to want to have your notes handy for this section, as I provided you a table that we'll be referencing throughout this discussion. So this is going to be a review of some of the fundamentals of acid-base chemistry from general chemistry. So a Bronsted acid is defined as a proton donor. So a Bronsted acid is defined as a proton donor. So for example, hydrochloric acid is a Bronsted acid as it donates H plus to our base. A Bronsted base can be thought of as an H plus acceptor. Ammonia accepts a proton from our acid to generate a conjugate acid. Now, acid-base reactions can be thought of as an equilibrium. That's what these reverse arrows are indicating. So this acid-base reaction is potentially reversible. And the position of this equilibrium depends not only on your acid and base, but on the conjugate base and the conjugate acid. So when the acid reacts and donates H plus to the base, we convert our acid into the conjugate base. Likewise, when our base reacts by accepting the proton, the base then converts to the conjugate acid. And by looking at the structure and stability of our acid, base, conjugate base, and conjugate acid, we can begin to predict the position of our equilibrium. Does that make sense to everyone so far? Does this look like review to everyone so far? Okay. So weak acid and weak bases engage in equilibrium or reversible acid-base reactions. So for example, if you have hydrofluoric acid in water, it will reversibly dissociate to generate H3O plus and F minus. So we can think of this process as a forward and reverse reaction. And the forward reaction can have a rate K1, so this is rate of reaction 1, and there can be a rate constant 2 describing the rate of the reaction number 2. And the equilibrium depends on the ratio of our forward reaction over the rate of our reverse reaction. So depending on Depending on the rate of each of these reactions, the position of our equilibrium will change slightly. Does that make sense to everyone so far? Does this theory look familiar? Perfect. So let's talk about K equilibrium and Ka. The equilibrium constant for the reaction of an acid with water to form hydronium and the conjugate base is a measure related to the strength of the acid. So K equilibrium provides a measure of the steady state concentration of each species at equilibrium. And in general, stronger acids have a larger K equilibrium, as we have a larger K equilibrium is directly tied to more H plus in solution. So K equilibrium is defined as the concentration of H3O plus and conjugate base over the concentration of acid and the concentration of water. Now, the concentration of water as a solvent does not change significantly. You may have noticed in many of the equilibrium constants that you were provided in general chemistry, this water term was neglected. That's because the concentration of water in these equilibrium reactions typically doesn't change substantially. And the concentration of water can be thought of as an almost fixed concentration. Now, the concentration of water can be estimated to be around 55.6 molar. And what we can do is we can rewrite a new equilibrium constant that accounts for this water term and moves this water term into our equilibrium constant expression. Ka is defined as K equilibrium times the concentration of water, which can be thought of as K equilibrium times 55.6. Now, if you have a solvent that is not water, then this equilibrium constant expression will change slightly. And instead of water and H3O plus, you'd have the solvent and the protonated form of the solvent. Now, Ka can range from 10 to the 15th for the strongest acids to very small values such as 10 to the negative 60th for the weakest acids. So Ka is formally defined as the concentration of H3O plus and A minus over the concentration of our acid HA. Does this make sense? Does everyone understand what Ka, the Ka values in the tables are representing? Now, and this is really important. Depending on your solvent, you will see and you will observe different Ka values. So this Ka term is solvent dependent. The general trend typically remains the same, but there is a strong dependence on the solvent that you use. So pKa is best thought of as the acid strength scale. So pKa is defined as negative log of Ka. Now here's where we're going to tie pKa to equilibrium. So the free energy at equilibrium, otherwise known as the Gibbs energy associated with your reaction, is related to negative log of K equilibrium, not Ka. So Gibbs energy can be related to the equilibrium constant for a given equilibrium set of reactions via the following expression. Now, what we can read from this expression is this idea that if we have a small pKa value, so if we have a small pKa value, What this in turn is telling us, when we have a small pKa value, we are dealing with a strong acid. pKa is directly proportional to the difference in Gibbs energy between the products and the reactants. So a small pKa value indicates a large Ka value and a strong acid. Just to give you a reference point, the pKa of water is about 15.74. Now, one other very important aspect that we can read from our pKa expressions has to do with the fact that Ka is directly related to the measure of the conjugate base strength, Kb. And we can write out an expression, for our conjugate base strength, Kb, that looks something like this. So Kb can be defined as the concentration of HA times the concentration of OH minus over the concentration of A minus. And as we recall from general chemistry, if we take Ka times Kb, we get Kw, which is about 10 to the negative 14th. One consequence of this relationship is that Kb is equal to Kw over Ka. So there is an inverse relationship between our conjugate base strength and our acid strength. So when we have a large Ka value, we end up with a very small Kb value. And if Kb is indicating our conjugate base strength, the main takeaway I want you to get from this discussion is that strong acids produce weak conjugate bases. Does that argument seem familiar to everyone? Does this argument make sense? Have you seen this idea and this set of expressions before? Does this look familiar to everyone? Okay, so building off of this idea that strong acids produce weak conjugate bases, if we look at hydrochloric acid, for example, hydrochloric acid has a pKa of around negative 7.0. It's a very strong acid. And as a result, because it's such a strong acid, chloride is a very weak conjugate base. So we have a strong acid that in turn reacts to produce a very weak conjugate base. Does this make sense to everyone? Any questions on this example? If not, let's keep going now. So there's a pKa table that I want you to reference. So I have it set up on a separate sheet just for my reference. This is a pretty common table made by the Evans group. It's quite useful. I also have a full version of this pKa table in Canvas. You're going to want to save this sheet as a reference because we're going to be using this a lot in our discussion of acid and base strength and equilibrium position. So you're going to want to make sure you have your pKa table handy. Remember that Ka and Kb are inversely related, and strong acids produce weak conjugate bases. Okay, so now that we have this table to work with, I've also provided you an additional table with some useful pKa values. that we'll also be using throughout this lecture. So these are just the reference sheets that we're going to be using. Let's talk a little bit about how do we predict an acid-base reaction using these pKa values. So pKa is related to the equilibrium constant and equilibrium concentration of each species. In acid-base reactions, the difference between the two pKa values, so taking pKa1 minus pKa2, is related to the ratio of equilibrium constants for each acid. So the difference in pKa values is related to the ratio of our equilibrium constants. Now, in general, a stronger acid has a smaller pKa value, and the greater the difference in pKa, the more of our conjugate base and the more of our protonated second component is present at equilibrium. To put it more simply, if the pKa value 1 minus pKa value 2 is less than 0, then the equilibrium is product favored. If pKa1 minus pKa2 is greater than 0, the equilibrium is reactant favored. So what are our labels for pKa 1 and 2? Well, pKa1 is our reactant pKa. While pKa2 is our product pKa. And if we take the difference between our pKa values, so pKa1 minus pKa2, that in turn is looking at the ratio of our equilibrium constants, K2 over K1. And in this case, so looking at this case for acetic acid and water, we notice that our difference in pKa values comparing our reactant and product is less than 0. Now, because our difference in pKa is less than 0, what that tells us is that this equilibrium overall is product favored. And as a result, in this acid-base reaction between acetic acid and hydroxide, this reaction and this equilibrium favors the product. You can also think of it as acetic acid is a stronger acid than water, and the equilibrium favors the reaction of our stronger acid to generate the conjugate base. That's another way of thinking about it. Does this idea make sense to everyone? How we can use the pKa values to predict the position of equilibrium? Does this make sense to everyone so far? Any questions on this idea? Can I get some responses in the chat that everyone's comfortable with how we both use our pKa values and which two pKa values we subtract? So you're only, for a given acid-base equilibrium, you're only given 2 of the pKa values because there's only the acid and the conjugate acid, right? So for our reactant, we are starting off with our acid, right? And in turn, our acid will react with our base and we generate the conjugate acid. So this expression compares the strength of our acid and conjugate acid, and whichever species is the stronger acid, the equilibrium will shift to the opposite side. So acetic acid is a stronger acid than water, so the equilibrium is product favored. The equilibrium shifts to the right. Does that answer your question? Perfect. So let's keep going now, and let's take a look at the following table, and let's rank the following substances in order of increasing acidity. So stronger acids, do they have large or small pKa values? Strong acids, do they have large or small pKa values? Small, yep. So which of these species is the strongest acid here? Which of these species? Acetic acid, yep, exactly right. Okay, so that's our strongest acid. What's our next strongest acid? Yep, 2,4-pentane with a pKa of around 9. What's our next strongest acid? Phenol, okay. And then finally, acetone is our weakest acid with a pKa of around 19.3. Does this example make sense to everyone? Perfect. So let's take a look at this next example. I'd like you to tell me which of the following anions is the strongest base. And I've given you these 2 pKa values. And recall that Ka and Kb are inversely proportional. So Kb is proportional to Kw over Ka. In other words, a large Ka and a small pKa leads to a small Kb and a large pKb. So then, with this idea in mind, would anyone like to tell me which of these bases is stronger? The one on the right, exactly. So let's walk us through our logic. So 1, acetone is a weaker acid, which in turn means that the acetone anion must be a stronger base. And that's essentially the only premise that we need to use for our argument. Acetone is a weaker acid, and as a result, it will generate a stronger base. Does that make sense to everyone? To make this implied premise explicit, we also know that the following diketone is a stronger acid, ergo the anion formed is a weaker base. Does this example make sense to everyone? Everyone seems to be pretty comfortable using pKa values to predict the position of an equilibrium. Let's keep going now, and let's try to answer the following question. Is it reasonable to use sodium hydroxide to deprotonate the following compound? Would this work, considering the following pKa values? Could we use sodium hydroxide for this reaction? And essentially what I'm asking is this equilibrium product favored as written? What does everyone think? Don't be shy to share your responses in the chat. Is this equilibrium product favored? Yes, yes. So if we look at the difference in pKa's, we clearly see that this diketone is the stronger acid, ergo the equilibrium is product favored. You can also think of it as the difference in pKa values, which is 9.0 minus 15.7. The difference in pKa values is negative, ergo our equilibrium is product favored. Does this example make sense? Perfect. So now let's look at a more sophisticated example. So nicotine exists either as the free base, monoprotonated, or diprotonated form. I want you to draw the monoprotonated form given the following pKa values. So your job essentially in this problem is to predict the position of the equilibrium considering the following two possible protonated forms that we can have. So the first form looks something like this. And I'd like you to predict which of the following species is favored at equilibrium. The first protonated form where we protonated our pyridine, or the second protonated form where we protonate our pyrrole nitrogen. Again, the pyridine and pyrrole nitrogens. So this should be a methyl group. There we go. So I'd like you to tell me the position of the equilibrium comparing these two protonated forms. And this is a case where rather than having our acid and base in separate molecules, we're looking at acidic and basic sites in the same molecule. So let's take about 3 minutes to work on this example, and I'd like you to tell me which of the monoprotonated forms is the predominant form at equilibrium. And we're already starting to see some reasonable responses in the chat. Let's really share your thoughts. And what I'd like you to do when you share your response is try to talk a little bit about your reasoning. your logic behind your solution. So we have one student in the chat proposing the equilibrium is product favored because the pKa value on the product side is higher. What does everyone else think? What does anyone have any input or feedback to that? Equally important to predicting the correct answer is providing an explanation. And I personally like this explanation. It invokes the data present. Does anyone else have a proposal for this problem? What does everyone else think? And really, don't be shy to share. There's nothing wrong with proposing an answer that's different from your classmates. The more responses we have, the more we can have a nuanced and full discussion of this problem. Does anyone else have a proposal? Yep, so we have a delta pK calculation, similar argument, but perfectly fine logic. The delta pK is negative, so this reaction is product favored. So essentially what we're saying in our argument is that this protonated form where we protonated our pyridine is a stronger acid. And as a result, the equilibrium is product favored. So what this tells us, what we have done in this example, and this is a really important example to keep in mind if we want to think about reaction mechanisms. So what we're saying quite simply is at equilibrium, this protonated form is favored. This protonated form is favored at equilibrium. So if we treat nicotine with an appropriately strong acid, and we just use one equivalent of acid, what we'll notice is that this pyrrole-like nitrogen will be protonated preferentially. So, depending on the structure and functional groups present in your molecule, you can choose and you can design and utilize an acid to selectively protonate one of your nitrogens. This is really important to think about because we are starting to differentiate parts of our molecule based on reactivity and properties. Does this example make sense? Does everyone see how when you treat nicotine with acid, that protonation of the top nitrogen is favored? Because if we protonate the bottom nitrogen when protonated is more acidic. Does this make sense to everyone? Can I get some feedback in the chat that everyone's comfortable with this? So when you go through and when you start thinking about reactions that are acid catalyzed, that use acid, I always want you to think, what are my pKa values and where are my protons ending up? What atom actually gets protonated? Because if you wanted to protonate this pyridine nitrogen in nicotine, you'd have to use another more forcing set of conditions. Okay, so I like this example. It's pretty fun. Now, what I want you to do now is look at the following structure for propanolol. Always have trouble pronouncing that name. And I'd like you to approximate the proton's pKa, and I want you to identify the most acidic proton. This is where you're going to need to use your Pka table, okay? You're gonna need to have these values functionally memorized for the exam because having Pka values of common functionalities on hand will not only save you time, but it's critical for assessing later problems in this class. And it's especially important in organic too, where we deal with a lot more anionic reactions. So I'd like you to take about 3 to 4 minutes, and I want you really to just look at your pKa table, find each of the functional groups in this molecule, find and label each of the major acidic protons that we need to consider, and then circle and identify the most acidic proton. Does everyone understand what I'm asking you to do in this example? So let's work on this for about 3 to 4 minutes, and don't be shy to type in the chat which proton you think is most acidic. For the pKa table that you'll need for this discussion, you'll primarily be looking at the embedded pKa table in the notes. I'll post a link to the full pKa table in this section of Canvas. So you'll see the link pop up later today. And if you have any questions working through this example, don't be shy to let us know. I'd be happy to address any questions or provide clarification. Let's keep working on this example, but I'd like to see some responses in the chat in terms of some protons that you've identified and some pKa values that you've assigned. And we'll discuss this example in about 2 to 3 minutes. So would anyone like to share some of their pKa values assignments? Don't be shy to share your thoughts in the chat or verbally. And that way we can help shape this discussion moving towards the solution. So we have an assignment for the alcohol as a pK of around 15 to 17. Okay. Would anyone have, oh, we also have an assignment for the amine with a pK of around 35. What other acidic protons do we have? what other potentially acidic protons do we have? The amine is around 35, yep. What about a benzylic or vinylic proton? What about a benzylic or vinylic proton? And what about an alkyl proton? Does anyone have those pKs from the table?
I think it's 9.9
Or which one?
for the double bonded ring, the benzylic, I think is what you said.
Let's check. Let's discuss this example, and let's start by looking at the pKa for our vinylic or benzylic proton. So if we look up a vinyl proton, our pKa is around 43. So then we'd assign this pK value to be around 43. It's a little less since we're dealing with an aromatic system, but this is a reasonable estimate for now. For our alcohol, if we go to our Pka table, for our alcohol, let's find an alcohol. An alcohol is a pK of around 17. Okay, so our assignment is perfectly fine there. For our amine, let's go check our amine now. So our amine has a pK of around 35. Okay. So what proton is our most acidic proton? We haven't considered this alkene proton, so let's look that up really quickly. Sorry, the alkane proton has a pK of around 50. So let's write that down. Okay, so what is the most acidic proton in this molecule? What is the most acidic proton in this molecule? What proton has the lowest pKa? The alcohol, exactly right. So the alcohol proton is our most acidic proton. Does that make sense to everyone? So we looked up each of the pKa values for each of our major potentially acidic protons. The proton with the lowest pKa is the most acidic proton. Does that make sense? Does this example make sense to everyone? Perfect. The only tricky part is you're going to have to be familiar with the pKa's in the Pka table. And don't worry, there'll be some tricks later on in the chapter to get relative acid and base strengths determined. So let's look at the following molecule known as L-DOPA, which is used in the treatment of Parkinson's. I'd like you to identify the 4 most acidic protons and arrange those protons in order of increasing acidity. So let's take about 3 to 4 minutes for this example, and let's apply what we've learned from the previous example to this problem. And don't be shy to share your responses in the chat for which protons are the most acidic. So I'm just going to label I'm just going to label our protons, and I'd like you to assign the pKa values to the four most acidic protons, and I'd like you to arrange the four most acidic protons in order of increasing acidity. And we'll discuss this example in about 3 to 4 minutes. And don't be shy to share your responses in the chat for your acidic proton assignments. And you can also share your pKa assignments and relative ranking of proton acidities using the annotate feature as well. And if you have any questions working through this example, don't be shy to ask them in the chat. And we'll discuss in about another minute and a half. Okay, so I'm gonna need your help on this one. So let's start by assigning pKa values. What would the pKa value be for proton D, which is a carboxylic acid proton? Carboxylic acid. So let's look at our reference table. So if we find a carboxylic acid right here, so this CO2H functionality has a pKa of around 4, right? So then let's assign that pKa to be around 4. Remember, this CO2H functionality is known as a carboxylic acid. Okay, what is the pKa of this amine functionality, which is an NH2 functionality? Well, one example of an amine would be an NH2 functionality. This has a pKa of around 35. Good, good. Okay. What about this alkane proton? So this is an alkane proton. What is the pKa value of this alkane proton? 50. Yeah, not easy to deprotonate for sure. Okay, what about this vinylic or what about the vinyl proton? What's the pK of a vinylic proton? Around 43. Okay, perfect. Okay, for these two alcohols, what is the pKa value of an alcohol, approximately? Now, keep in mind, these aren't just normal alcohols, they're phenolic alcohols because they're connected to an aromatic ring. Remember when we looked at phenol? What is the pKa value about for a phenolic alcohol? Phenolic alcohol, this proton right here. Let's take a look. Let's take a look. So if we go to our supplementary table, do you notice how if we compare an alcohol and a phenolic alcohol, there's a pretty huge difference in pK? So what's the pK of a phenolic alcohol? 9.9. Okay, so these pKa values would be 9.9. If you really wanted to split hairs, here, B would technically be a little bit more acidic than A. And we'll be able to talk about that once we talk about resonance and inductive effects, as well as substituent effects. For those wondering, why is a phenol so much more acidic? Well, if we think about a phenol, if we remove the proton, we end up with a highly stabilized anion. And because our anion produced is so stable, it's less difficult and there's less of an energetic penalty to remove this proton to generate our anion. Does that answer your question for why phenols are more acidic? We'll talk more about this later. For now, we're just developing using the Pka table. So for our ranking, we have proton D, which is the most acidic, protons A and B, which are about equal to each other, and then finally proton C, which is the least acidic in our top 4 list. So this is our top 4 list for the most acidic protons. I would write A and B as equal, just because it's so close that it's going to be very hard to differentiate these two protons from an acidity perspective. Does this example make sense to everyone? So, key takeaways. You need to know your functional groups and you need to know your pKa's from the table. So these exercises are helping you learn them via practice. And that's what I recommend. Rather than flashcards, actually do relevant examples that use functional groups, that use pKa values. And that's how you really integrate the material in the same kind of problem-solving process that you're going to use for later problems in this class and on exams. Any other questions before we close out this example? If not, let's keep going and let's talk about something that's a little bit interesting now. L-DOPA is an amino acid. We're still talking about L-DOPA. Amino acids commonly exist as a zwitterion in solution. They contain both a positive and negative charge. Using your pKa table, I'd like you to indicate the most acidic proton and the most basic atom. And then I'd like you to draw the zwitterion for L-DOPA. So this compound is in equilibrium with another zwitterionic form. So I'd like you to identify the most acidic proton and then the most basic atom, keeping in mind that a base must have an available valence for bonding, and it must typically have a lone pair capable of abstracting a proton. So let's work on this example for about 2 to 3 minutes. So I'm going to label some atoms once again: A, B, C, D, E, F, G. I'd like you to tell me what is our most acidic proton, what is our most basic atom, and I'd like someone using the annotate feature to try drawing the Zwitterion after this acid-base reaction occurs. And we'll discuss this example in about 2 to 3 minutes. So we have a preliminary assignment that A is the most acidic with a pKa of around 4. Okay. Now, what's the most basic atom? Let's think about that, and don't be shy to share your responses. Keeping in mind, the most basic atom must typically have a valence available for bonding and a lone pair that is able to abstract our proton. So even though G is the least acidic atom, it doesn't necessarily mean it's the most basic. So I see some proposals for C. Yep, that seems reasonable. C has a lone pair and it has a valence available for bonding. Okay. So then, how do we know if we compare C versus E? How do we know that C is more basic? How do we know that C is the most basic? Well, what we can do is we can look at the equilibrium. So if we have an amine and we compare an amine to its protonated form, and we have an alcohol and we compare an alcohol to its protonated form, the stronger base will have a stronger or weaker acid. The stronger base will make a strong or weak acid. Weak. The stronger base would make the weaker acid. So then, let's look at our pKa table. Let's look at our pKa table. What is the pKa of a protonated amine? What is the pKa of a protonated amine? Well, let's find it then. Protonated amine. So we're not looking at the amine section anymore. We're looking at the protonated amine, otherwise known as an ammonium salt. And what's the pKa of an ammonium salt? 9 to 11. Okay, what about a protonated alcohol? You're not looking at the alcohol anymore. If you're looking at a protonated alcohol, where is it? Where is it? Let me go to the supplemental table. Yeah, that's close enough. A protonated alcohol can be approximated similar to that of a hydronium. And what's the pKa of a protonated alcohol? Negative 1.74, exactly right. So then, which species is a stronger base, an alcohol or an amine? What's the stronger base, the alcohol or the amine? wait, so we said a strong base makes a weak acid, right? So what's our stronger base, our amine or our alcohol? The amine is our stronger base. Does that logic make sense? Does that logic make sense to everyone? Okay, so now what we're going to do is we are going to transfer a proton from our carboxylic acid to our amine. So now all we have to do is draw the product after proton transfer. And the reason why this equilibrium favors the product is, as we can see, the carboxylic acid is more acidic than our ammonium salt, right? Does everyone see how the carboxylic acid is more acidic? So that's why this proton transfer occurs. Just like in the example with nicotine, right? So does this example make sense to everyone? Does this analysis make sense? So we can figure out the acid strength using our Pka table. For our base strength, we need to consider which conjugate acid is the least acidic. So to tie this all together as our last interesting example, I'd like you to use your Pka table, and I'd like you to tell me which of the following organic bases would be reasonable to use to generate the following anion. So given the pKa value for this acetylide, this acetylene proton, which of these bases would be reasonable to use? Keeping in mind that if this lithium is drawn, I'm referring to the anion. So I'd like everyone to take a moment and use their Pka tables, and I'd like you to tell me which of the following bases would be suitable to generate the following acetylide anion. So what bases can we use? And my suggestion would be to look up the different conjugate acids and check to make sure that your conjugate acids are weaker than acetylene. So let's put some labels to this. So we have A, B, C, D, E, F, and G. And I'd like you to tell me which of these 7 species are acceptable bases. Which of these 7 species are acceptable bases? And we'll discuss this example in about another 2 to 3 minutes. And I'd like to see at least a few responses in the chat before we discuss. And you don't have to find all of them, but I'd like to see your progress in reporting which bases are acceptable to complete this reaction. Does anyone have any proposals that they'd like to share? Remember, you're looking up the pKa of the conjugate acid and making sure that the conjugate acid is less acidic. So just for F, so F, the conjugate acid looks like this, and it has a pKa of around 4. Is acetic acid more or less acidic than acetylene? Just to follow up on that student question. Acetic acid is more acidic, so we probably can't use acetate then. We have a suggestion for C. Okay, so let's show the conjugate species. And what's the pKa of this alkane? What's the pKa of an alkane? 50. Is an alkane less acidic than acetylene? Yes, so C would be a perfectly fine answer. So that's 1. There are a few more actually. Would anyone have another proposal? D, yep. D would be perfectly fine. Why is that? Well, if we think about an amine has a pKa of around 35, okay? What else? What else? We're on a roll here. We're almost finished. We have a few more to list. We said C would be a viable base. B is also viable by extension because the alkane proton has a pK of around 50. Okay, what else? For A, so A, we did correctly note that an alcohol with a pK of around 17 would probably be a no-go. Looking at dimethyl sulfoxide, this is known as the dimsyl anion, and it's actually pretty basic. Let's show why that is. Let's do an analysis. Why is the dimsyl anion acceptable? Well, let's look at our table. Let's look at our table and let's really look and try to find it. So looking at the sulfoxide, what is the pK of dimethyl sulfoxide? 31. So then, this one has a pK, the dimethyl sulfoxide has a pK of around 31, so it would be acceptable, yes. Okay, is there anything else? What about sodium hydride? Sodium hydride, what about hydrogen? What is the pK of hydrogen? What is the pK of hydrogen? That's a little bit of an odd phrase since it's not quite an equilibrium process, but hydrogen has a pK of around 36 from our table. So could we use sodium hydride for this reaction? Yes, exactly right. The reason why I like to find these examples is because if you're actually asked to run or screen or test an acid-base reaction, you want to make sure that you're using bases that can actually deprotonate your molecule. So you really don't want to be in a lab trying to run a deprotonation reaction. You dump in a base that isn't strong enough and you're wondering why the reaction doesn't work. So this is just helping you design and plan reactions and understand why certain bases are chosen for certain reactions. So this is a good example to wrap up today's lecture on utilizing Pka values. What we're going to do is we're going to take a 10-minute break and then we're going to resume for laboratory. And we're likely going to lecture for about another hour and a half in lab, just so that way we're on pace with the material.